Today we study X26Q Maxwell-Boltzmann distribution and the specific heats. You can download the PDF file for this lecture from here, the KPOPE Digital Library. The address of the KPOPE Digital Library is kpop.org, kpope.org. Table of contents has X series. If you click this and scroll down to find X26 Maxwell-Boltzmann distribution and the specific heats. The main textbook is contained in here, X26, and you can watch lecture video in Korean by clicking the button next to K, and if you click the button next to E, the lecture given in English is available. You can return to our K-pop digital library by clicking here. And if you have not subscribed K-pop YouTube channel yet, so please click this and click the button for the subscription. Here is a K-pop collaboration YouTube channel. The address is youtube.com/kpop. Okay, let's begin with our lecture. Today's lecture is for X26Q Maxwell-Boltzmann distribution and the specific heats. Number one, why do we need to evaluate the Gaussian integrals in n dimensions to study the Maxwell-Boltzmann distribution? You will find it. We need to evaluate this to evaluate the probability of finding a molecule with a certain velocity in the phase space and average value of the kinetic energy from which we can derive the ideal gas equation. And from this relation, we can identify how the average kinetic energy of a molecule is computed, and we can find that the Maxwell-Boltzmann distribution has a symmetry to satisfy the equipartition theorem. Okay, let's begin with the Gaussian integral. Evaluation of Gaussian integral directly in one dimension is not trivial. Instead, because this is a number, we square this integral and then take the square root. In that case, the integral becomes the double integral evaluated on the two-dimensional Euclidean space. The evaluation of the integral becomes trivial if we make use of the two-dimensional polar coordinates. In that case, the dx dy can be converted into area in the two-dimensional polar coordinates as r dr d theta. The complete decoupling of the radial and angular integral shows that this angular integral is the 2 pi and this radial integral is 1/2. To find this pi, after taking the square root, we find the value of this integral is square root of the pi. Sure, it is a positive definite, so it is impossible to have minus square root of pi. We multiply this pi, square root of pi by n times, that is equivalent to the product of n such Gaussian integrals. We can extend this method to the n-dimensional Euclidean space, and the integral reduces this form. And because this is a square root of pi, the answer must be the nth power of the square root of pi. We can change the variables to make use of this Gaussian integral to evaluate a little bit different integral with positive constant alpha as a parameter. And we can change a variable by taking square root of x equals to t, something like that. Then we eventually have a overall factor, and this one is to be replaced with t, and this dummy variable, integral variable, can be replaced again to x to find that this is a square root of pi. As a result, this integral is a square root of pi away. If we repeat that calculation, the general form of this integral is eventually expressed as square root of pi over a to the nth power. We'd like to extend this one to evaluate the average kinetic energy of a molecule in an ideal gas system. The kinetic energy is identical to the total mechanical energy of a free particle because we assume that the ideal gas does not have any structure in it. The kinetic energy is then expressed in terms of 1 half mv squared, and v squared can be divided into three pieces, the xyz component of squared velocities. We assume that the gravitational force is negligible in a system of gas that has tiny mass, and the difference between the bottom and the top of a container is negligible to consider the change in the potential energy. Then the symmetry of the isotropy of the isotropic symmetry of the Euclidean space guarantees that these three values must be symmetric. Sure, if I select a single molecule, I don't know what happens. But if I have a large number of molecules of order Avogadro's number, then the average value will be certainly the same for all three components. So we next assume the Maxwell-Boltzmann statistics for the molecule's kinetic energy. And in a thermal equilibrium at temperature T, we use the Boltzmann factor. Boltzmann factor is energy divided by kBT, where kB is the Boltzmann constant and the T is the temperature in which a statistical system is in equilibrium. And the probability of finding a system with the energy E is proportional to this exponential minus energy over kBT. Because the probability has the total sum is unity, this requirement can determine the overall factor that the normalization constant C. While the summation over I is a little bit abstract, in a system of ideal gas molecules, the distribution can be, the summation index can be replaced with the integration of velocities. And all three Cartesian components of the velocities could range from minus infinity to plus infinity. So as a result, we keep the C, the normalization factor C, undetermined, but we'd like to impose the distribution based on the Boltzmann factor to make the sum of the total sum over the all possible states of a velocity distributed over three components of velocity. The all sum of all possible states should be fixed to be unity. We remember how to evaluate the Gaussian integral and how to convert this kind of integral into Gaussian form. So we change the variable. A little bit complicated variable can be replaced with a simple parameter a that is a positive definite. And then we like to make use of the properties that we have derived to evaluate the Gaussian integrals. Uh, First of all, we can think about the kinetic energy distribution. That the distribution can be summed, and we know how to convert this one in terms of change of variable. The final result must be a c that is the undetermined normalization factor, and we have a square root of pi over a cube. Finally, this c is completely determined the reciprocal of this factor. If I substitute this explicit value for a, then we obtain the over normalization factor. We can check the calculation by substituting this explicit value for c in here. Finally, if we reach the point that the probability, sum of the probability of all possible velocity state of a molecule must be 1. Next, we make use of this probability distribution to evaluate the average value or standard deviation, something like that. Statistical business has begun. So, if I have some function that is just like this, we do not have angular dependence. Instead, the magnitude of the velocity, the speed, is our concern. Finally, if I want to compute the kinetic energy, that is 1/2 mv squared, the v squared should be averaged over if I want to. But this is not the v squared that to be averaged, but it is just a reparametrization of a three-dimensional Euclidean space from the Cartesian components to the radial, the three-dimensional polar coordinates. This is the radius r squared dr and d cosine theta that runs from -1 to 1 and the azimuthal angle integral over 0 from 0 to 2 pi. Because the integrand that includes the Jacobian of radius, integrand is independent of angle. This angle is just 4 pi. 2 pi comes from the azimuthal angle, and the polar angle integral yields a factor of 2 to have 4 pi, that is a solid angle in 3 dimensions. Finally, we can make use of this normalization constant, and would like to repeat the calculation is an integral as a single variable, the speed instead of velocity. Angle has been integrated out, and we use the change of variable to simplify this integral in this form. What's that? This power can be expressed as a 1/2, and that is a 3/2 minus 1. And this is the parametrization we have developed for the gamma function, and this is identical to the definition of gamma function. We know the gamma function has a special property, so gamma 3/2 should be 1/2 multiplied by gamma 1/2, and the gamma 1/2 is identical to the Gaussian integral, and that Gaussian integral is a square root of pi. Therefore, this is a 1/2 of square root of pi that cancels this over factor to find out the unity as expected. Now, as the last step, we want to compute the average velocity squared or average speed squared for a molecule, but depending on the Maxwell-Boltzmann distribution. Now we convert this x dot square in terms of this dimensionless parameter t and this over factor a. Finally, at the end of the day, we will find gamma 5/2. Again, we keep using z gamma z equals z plus 1 gamma z plus 1 is product of this. So we have 5/2, that is a 3/2 multiplied by gamma 3/2. This one is to be replaced with this, and then finally we have 3/4 of the square root of pi. If I substitute this value in here, final value is this. That is 2 cancels, and we have a 3 kBt divided by m. If I make use of this one, we have m times x dot squared equals 3 kBt. Let's see, this is a vector squared, and we can make a replacement x1 dot squared, x2 dot squared, x3 dot squared. Vector of 3 may cancel if I apply the symmetries of the 3 axes neglecting gravitational force. Then we have an equipartition theorem is satisfied by this Maxwell-Boltzmann distribution. All right, so this is equivalent to the equipartition theorem. So the Maxwell-Boltzmann distribution respects the equipartition theorem. That's very, very important. And eventually, because this replacement has been achieved by the Maxwell-Boltzmann distribution, it is straightforward to satisfy the ideal gas equation called PV equals NKBT. Number 2, consider N molecule A and another N molecule B. And we consider, we supply the heat, delta Q. And the sample A has been raised in temperature by delta A, and the same energy is supplied, keeping the volume constant. Then the raise in the temperature of B has a relationship with the TA like that. From here, we can determine the delta TB, change in the temperature of the B molecules, is 3/5 of the change in the temperature of A. The heat capacity at constant volume can be computed with the delta Q over delta T, with keeping the volume the same. Because of this relation, we can replace this one in terms of this, express this in terms of the delta Q over delta TA that is identical to the CV of A. So we have a special relationship between the A molecules and B molecules. So this one from which we can determine that whether this type A and type B, they are either monatomic or diatomic or polyatomic gas. Based on this idea, we have a ratio of 3 and 5, and the one is diatomic and the other is a monatomic. So A is monatomic and B is diatomic. 3. Find the gas equation for an ideal gas consisting of n molecules under adiabatic process. In an adiabatic process, we do not exchange any heat. And then I steal the ideal gas, satisfy the ideal gas equation. If I make a differential of the both sides, this is still identity because they are the same. Both sides can be expressed in terms of this because we keep the number of molecules. So this is proportional to the dt, and the other vector is a constant. Right hand side is we can apply the Leibniz rule for the product differentiation, the differential, computing the differential of the product, and we have this. At constant volume, we can compute the heat capacity at constant volume because in this manner, the heat supplied is directly converted to the temperature change of this gas, because according to the first law of thermodynamics, that there is no work done by the gas. So this relation works. At constant pressure, the dP equals 0. So this one vanishes and only PDV survives. And at constant temperature, the differential of PV is identical to PDV. And then that is identical to the temperature change at constant temperature. So the relation between the heat capacity Cp and Cv, so the difference is due to the work done by the gas. And the work done by the gas is expressed as because of this identity. If it disappears, the PDV is just the nkb dt. Because of that, heat capacity at constant pressure multiplied by the temperature change should include this PDV. That amount can always convert it with nkb dt. As a result, we have a simple relationship between Cp and Cv in this manner. In an adiabatic process that does not involve any heat exchange, there is a special relationship between the internal energy change and the work done by the gas. Because of this identity, the temperature change can be always expressed. This one can be expressed in terms of this, and that temperature change can always be expressed as negative of pressure over Cv multiplied by dV. Using this manner, these kind of identities, so you can obtain various relations. At the end of the day, you will find that an adiabatic process, P multiplied by V with gamma, whose power, this power gamma is Cp over Cv. Okay, that's it for today. Thank you.